very nice introduction. And I'll get my presentation started. So today I'm going to talk on the topic energy efficient additive manufacturing of epoxy thermosets and the composites. Okay, so first let me introduce myself. So I'm Ruochen Liu, PhD student from Department of Material Science Engineering and from Dr. Shiren Wang's group. And it's my pleasure to present today. So let me start it with the introduction. So currently fiber reinforced composites have been widely used in a variety of commodities and energy industries, and as well as automobile industries, aviation industries. So it's just a very nice material to use and very strong and lightweight, has a lot of advantages. However, one of the challenges in composite manufacturing, especially, is the very expensive labor and energy consumption. So, for example, if people in the industry want to manufacture a very large piece like an airplane fuselage, they have to use extremely large autoclave for curing, and the curing process takes hours, and very sophisticated temperature profile has to be used here. And besides that, the composite here, people manufacturing has some limitation in that the shape of the composites is very hard to manufacture into a complex structure. And then if people want to make it complex, they have to also make a complex mold before they can processing the composite manufacturing. And then after the large piece are manufactured, the transportation is also a problem. And so here we want an energy efficient way to in-situ fabricate the composite material in a mold-free manner. And then at the same time, we want it to be like flexible in structure design. So here, one of the interesting solutions to this is by using the frontal curing method in 3D printing technology. So I'll here introduce the frontal curing. So it is a localized curing that occurs in a self-propagating way, which can be initiated by a transient energy input, as shown in this video. That let me hear. So when there's a energy input here, triggers the polymerization process, the reaction can propagate along the whole part without any external or extra energy input, which is very convenient and also possess all of these features, which is desirable for manufacturing. So here in 2018, groups in UIUC have reported using the frontal curing method to fabricate a variety of parts. Especially here, what is interesting is that they use it as 3D printing. They use it in 3D printing technology. So here, they're using dicyclopentadiene molecule to do the manufacturing, and then after they calculate the energy consumption, it was reported that the energy consumption for this manufacturing technology it's almost ignorable compared to the conventional curing method, and also it is imaginable that due to its feature that's a one trigger, and then the whole part can be polymerized or cured, so that when the part size goes too large, when the part size getting larger and larger, the energy consumption per volume will be significantly reduced. So that's a very interesting topic. However, when talking about the material they're using, the dicyclopentadienyl, there are some limitation in this material. It's one of the most restrictions for its application here is first in existing market. So the market size of this material is relatively small compared to epoxy resin, and then also the dicyclopentadienyl is very toxic in use, and not compared to this epoxy resin, and which is a good material to work with, which is non-toxic, and they are good in mechanical properties, and also they have a lot of other benefits in terms of their chemical resistance and thermal resistant properties. So then we're thinking maybe epoxy resin will have a more impact if we can make it available for frontal curing using a 3D printing technology. However, one of the challenges remaining for using this material is that the traditional curing agent, which can be shown here, the curing agent can cure the part, but the heat releasing profile is not desirable for the continuous self-propagating reaction. So for desired heat releasing profile, we want it to be a burst of heat releasing, and then the reaction can be sustainable. So one of the solutions people have been found is that using the radical induced cationic frontal curing to do the to manufacturing, to fabricate this epoxy composites. And we can see here the heat releasing profile is very desirable, which is a burst of heat release. And then we can see here the propagation velocity is very high compared to DCPD and other existing like traditional curing agent. However, the problem here also appears that it's the propagating temperature, which the temperature the polymerization occurs, is very high, so that the resulting material is turning dark, which means there's decomposition happening due to the high temperature, and as a result, the mechanical property is not desirable. So here, so if we want to do making this epoxy material as a to manufacturing the epoxy composites, here the first thing we studied the concentration effects on the frontal temperature. In that we think that by reducing the temperature, the frontal temperature, we can significantly increase the part performance, and also make it compatible to the additive manufacturing process. So as we tune the concentration of the initiators, we were able to significantly decrease the frontal temperature, and also at the sacrifice of frontal velocity, but it still is 4 centimeter per minute, which is compatible with the 3D printing process. So, and we can see here that the color of this part produced by different initiator concentrations is very vividly contrast. So using lower concentration will appear like a dark yellow appearance, making it a very good mechanical properties. And then we, by tuning the processing parameter here, with tuning the extrusion pressure of the printing process, we can also significantly lower the frontal temperature, and then also the frontal velocity is reduced as as a companion with the frontal curing temperature. So here, we also compared how the frontal temperature affects the performance of the material. Here we found that the tensile strength significantly increased as the frontal temperature is reduced, so which is desirable for the printing process as well as the part performance. So here we demonstrate some printed part with the previously mentioned technology. So we here use a single nozzle design and a dual nozzle design to print continuous carbon fiber reinforced epoxy composites. So by using these two different geometry of nozzles, we were able to tune the fiber volume so that the frontal curing temperature, the frontal curing speed, and the mechanical property can be tuned here. So here are some of the parts we printed. And also, as we compared our printed results to existing additive manufacturing of carbon fiber composites, our results shows better performance, which is nice, and compared to the existing continuous carbon fiber printing process. And then also, as a very interesting fact, so we compared our process energy efficiency to existing method, which shows very interesting energy saving property of our printing process, which is what we intended to do at the beginning. So also we calculate, we projected if our manufacturing method is applied to the industry, the energy saving is significant compared to using DCP dicyclo pentadiene as a resin, in terms of because that the epoxy is like more commonly used and have a larger market size. So and also we are able to model the printing process using console software. So here, by comparing our model with the experiment results, the model shows good match with the experimental results. And I think with this model, we were able to, in the future, if we want to change change resin or change some of the parameters of the process, we were able to study it both in the model and also in the experimental way. So here I will conclude. At first, the frontal curing assisted additive manufacturing demonstrates the energy efficient and versatile manufacturing of this epoxy composite, and then it shows good mechanical properties. And then we also the frontal curing characteristics and the printed part can be tuned by the printing parameters and the composition of the epoxy inks. And then we were able to numerically model the additive manufacturing process by coupling the reaction kinetics and the heat transfer model. And this is good for future numerical analysis. So, and at last, I acknowledge our group and also Dr. Zimeng Zhang, and who works with me in this project, and then my advisor, Dr. Shiren Wang. So yeah, with that, I'll conclude my presentation. Thank you.
Thank you so much, Ruochen. Yeah, any questions?
Yes, I have a question, if you could hear me.
Yes, please go ahead.
Yes, you focused on the manufacturing and the cost of that for the materials. What is the relative cost of the raw materials relative to the manufacturing cost? Do you know that?
Production of the epoxy resin, you mean?
Well, the cost of the carbon fiber and resin.
Yes, that's a good, very good, interesting point. Sorry, my light turned off. Yeah. So as here we are focusing more on the manufacturing part, as you said, yes. And the cost for the resin and the carbon fiber composite, although it's not our consideration, but it's true that they consume extremely a lot of energy during their manufacturing. So, but here, as I said, the fabrication of the composite itself, the manufacturing process itself consumes a lot of energy, which is the problem we're tackling now. Although I think it's also to reduce the overall energy footprint, carbon footprint, we also need to focus on the whole process from the, as you said, the carbon fiber manufacturing, or even go trace back to the oil industry. However, here we are focusing more on the manufacturing part, manufacturing of the composite, this part. Yes.
Thank you.
Thank you.
I think Dr. Joe Sabo has a question. Joe, and then Dr. Bashar write down the question in the chat box. Joe, please.
Yeah, okay, thank you, Louise. So also a question on the cost. I think it was slide 11 or 12. I apologize, I came on late, but I don't know all the acronyms. Yeah, that's one more, forward. The cost, I don't understand the difference. On the bottom is a flat line, and what are the other symbols? I don't understand which ones were which. I came on late,
okay.
So it's very interesting. But the energy savings here.
Yes, sorry, I kind of go through very fast here. I can explain. So here at the bottom, the blue line, we project the use of dicyclopentadiene as a resin for manufacturing of the part. It's relatively flat because the market size is very small. And here for this orange and red ones, we're comparing two different sizes printed part, different sizes being printed, and then how they consume energy in the coming years. So this is how the solid red and orange are representing. And here the dashed part is just the material consumption that from the current market information. So this is the material consumption, and here is the solid one is the manufacturing energy consumption. Yes.
Right. Okay. Sure. I can see that the material costs are relatively flat. Then, what is the main reason why you project higher savings 3-4 years in the future?
If I understand right, you mean the slope? Is that what you?
Right. Is it just because the market size is growing that you will save so much energy, or what is the reason for higher savings in year 2024, 26, and so forth?
So I think the reason is that the market is growing for the consumption of this typical material, so that and if we replace the whole manufacturing process as the energy saving ones, so the consumption of energy will also as well go higher. I mean, the saved energy will go higher, and I hope that's answer your question. It's a projection of the material manufacturing process replaced by this frontal curing method. And we have published the paper in recently last on November, and in that paper we have a detailed explanation of how it's calculated and explained. I think better than what I said maybe right now. Hope that.
I will consider that. Very good. Thank you very much.
Yeah, thank you. So okay, I saw that there are questions in the chat box. So I'll repeat that to the audience first. So Dr. Shiren Liu asked, in terms of tensile strength, how does this compare with epoxy resin cats by traditional method? I'm sorry, what do you mean by epoxy resin cats? So can you explain a little bit about the question?
Sergeant?
Yes, you talked about the frontal curing method, and I was wondering that compared to traditional 3D casting or even 2D casting methods we use when we make these plastic parts, do you notice a tensile strength difference? So I'm thinking, is the difference, does it matter? Does it make a difference on the method of making these parts, or there's a slight difference? Like, so if we do mold injection, right, we may see a difference in tensile strength compared to temperature, 2-degree temperature gradient casting methods. In some cases, we see no difference. So the tensile strength is independent of the method. So in your front curing method, do you see a difference in physical properties compared to traditional methods, or no difference?
Yes. So as I understand, the tensile strength is affected by a lot of factors, but for solely what our experiment, what I observed from the experiment, the frontal curing method has the comparable tensile strength as traditional ones. Although the molding process right now is like more for this part with less defects, because our process is still in its prototype. But I think in terms of the material property between these two methods, I don't see much difference in the experiment. Yes. And
thank you.
Yeah, and the second one is this manufacturing parts in this similar to traditional method in terms of speed and instrument casting cost. Okay, so here we simply use this 3D printing of this using the frontal curing method. So if we were to compare this to traditional method in terms of speed, I would say the speed would be significantly increased, because for traditional we need to like mold, and then as I said, there are extensively long period of heat treatment, and it usually has hours or even days. However, for our method, the printing speed here I show here is like some centimeter per minute. So in that case, if we want to fabricate, it depends on the part size. So for the size we were producing, and for medium size, I think it's more faster. However, if we are talking about some airplane fuselage, I think we need to take into account the manufacturing of like mold and the whole process. And still, I think that needs to be further researched about. I think that's a good question. Yeah.
Thank you.
May I have a question, Ruochen?
Yes, please.
Just in this 3D printing, is that easy to clean your nozzle?
As long as
the viscosity is very low, right?
Yes. So I think I think that's a good question, because from my experiment, I came across that nozzle is jammed by the frontal curing propagates through the nozzle, but it seldom happened because the heat releasing during, if the reaction propagates into the nozzle, the heat release will be significantly higher than it's on the substrate. So it means that the front seldom penetrate into the nozzle. However, if it's jammed, it's a problem. Yes, because the resin it's cured. So yes, I think that that sometimes happens. Yeah.
Do
And-
you know what's the temperature
The temperature of the
of the printing during
Yes.
the printing processing?
yes. So the front temperature here is the reaction at which it's the reaction temperature at which the reaction propagates. It's around 200 to 300 degrees C. So that's a very high temperature. Yeah.
Any other questions for our students?
I have one more if you doesn't mind.
Oh,
Yeah.
yes, please.
Okay, you said something that your frontal curing method takes traditional 3D printers. So are you saying that you take the traditional manufacturing printer and use it as is, or do you guys make a modification to the printing port because of the extrusion pressure, the temperature, and all that? Would that be identical between your methods, or do you guys modify that and then use it, or just use it as is?
We use the commercial printers. It's a bio printer. We just modify the nozzle and very simple modification. But the parameters, we use the commercial software, which yes, we use the commercial one.
Okay, thanks.
Yeah.
Any other questions for Ruochen? I assume the silence means you know. Let's give Ruochen a round of applause.
Thank
Yeah.
you very much.
Thank you so very much, Ruochen, for your beautiful talk. Yeah.
Thank you.
May I share screen?
Okay, I'll stop share. Yeah.
Can you see my screen? Can
Yes,
everybody?
Louise, we can see your screen.
Okay. Our next speaker today actually is a faculty member. Before we moving on, I must apologize. I did not communicating with our second student speaker very well. I'm sorry for that. So we have a faculty member who is volunteer to take his place.